Hey, it's Miss Murphy. How are you? Good. Okay. Oh, I hope you're good. Great. I'm doing all right myself. Just making lots of videos to try to help you guys. So we are maybe a last video for Lewis structure, molecular geometry, inter, and that should have been the last thing we talked about. And now we are going to take a deeper look into intermolecular forces, commonly referred to as IMFs. Once again, please write down what I write down, because I'm only going to write down what is important. And we're going to simplify it for you. All right. So I'm trying to share. There we go. Okay. So once again, we will title this nope, I don't like the way that looks. Intermolecular forces, right? You should have just been introduced to these. We commonly refer to them as IMFs. Recall, they are not bonds. They are attractive forces. They are weaker than bonds, and they are attractive forces between molecules. So it's what it holds one molecule in a solid or a liquid together, right? They are together. What holds them together? Intermolecular forces. Gases are far apart. Nothing is holding them together. They do not have intermolecular forces. Solids, tightly packed, right? Tightly packed, rigid, strong IMFs, okay? If we add heat, we kind of overcome those attractive forces. We end up with liquids that they can roll over each other, but cannot separate. All right, so you need to think about what Miss Murphy is writing. Liquids can roll over one another. That's why they can pour, but they don't fly apart. Okay, solids do not pour, right? I cannot pour that solid. I drop it. It doesn't flow. My coffee will flow. The particles can roll right over each other. So the attractive forces aren't so strong. So here we have strong attractive forces. Here we've got somewhat weaker attractive forces. We'll get there in a minute. If we continue to add heat, well, what happens? That means we have molecules that are totally spread apart, not connected at all, right? There are no IMFs. There are no forces of attraction in our gases. So when we talk about IMFs, we are talking about solids and liquids, and we are talking about the forces that hold the atoms or molecules, whatever that particle might be, depending on the substance. We're talking about the forces that hold them together. And we will see that liquids have weaker IMFs than do solids, okay? All right, so an IMF holds one thing to another. Just like an interstate connects states, an intermolecular force connects molecules. Let's look at the type. We've got London dispersion. This is the weakest. It's present among all molecules. Okay. Only force between nonpolar molecules. Oops. Okay. Okay. All right. So for example, if we have an H, right, that's H2, it is perfectly nonpolar. And we have another HH, right, which is perfectly nonpolar. The attractive force between these, well, there really wouldn't be one, it's a gas, but if there was, it would be a London dispersion force because we have two nonpolar molecules, right? If we have a carbon dioxide, which is linear and its dipoles cancel. For H2, there are no dipoles, right? There are no dipoles, right? We could see this where we have even sharing of electrons. Oops, excuse me, guys. Then if I had another carbon dioxide molecule, right? And we have an even sharing of electron. Our London dispersion force is this right here. I'm not going to get into more of what that is. If you want to ask, you can, and I can, but I'm not going to do that. The point here, guys, is that we have nonpolar with nonpolar, and the only force here that holds one particle to another are your London dispersion forces. Those are very weak. Okay, the next type is a dipole force of attraction. And that's when we have polar, those are forces between polar molecules. Dipole forces are forces between polar molecules. They are stronger than London dispersion. And let's look at why. Well, let's think of what do polar molecules have. They have dipoles. So let's draw a polar molecule. Let's draw H2S, right? It's going to look like this. Well, recall, let's look at our bond dipoles. Here's our partial negative. Here's our partial positive. Here's our partial negative. Here's our partial positive, right? I think we could see that we have some sort of a magnet here with a partial negative end there, partial positive end here with a polar molecule. Where we have one, we have another. So let's draw another molecule and let's put the S here and his electrons here and the H here and the H here. And let's draw our arrows. And let's see that the S again is partial negative and the S again is partial negative. And down here we have a partial positive and a partial positive. Let me finish my arrows here. Okay. And where is the attraction? Where is the intermolecular force? Is the attraction between this partial positive and partial negative, right? So that's the attraction that would hold this molecule to this molecule, right? And we see that we would have this partial positive end here attracted to this partial negative end here. And this is our dipole, partial positive, dipole, partial negative of another molecule force. And you see why it's stronger. It's stronger because these are charged particles, so the attraction is greater, right? There's not attractions between particles that don't have an electric charge. But if I could put positive and negative charges on these, they would pull together. So that's what we would see happening with this here, okay? Now, and one more step would be hydrogen bonding. Okay, that's the last type of intermolecular force. Now, do not be fooled. It says bonding, but it is not a chemical bond. At one point, they thought it was because it's very strong, but it is not within a molecule. It holds molecules together. So it is a force of attraction. It is the strongest IMF. It is a special type of dipole-dipole. All right, as a special type of dipole-dipole. And it occurs, and I'll explain why, when occurs, let me make this bigger again, sorry, occurs when H is bonded to nitrogen, oxygen, or fluorine. Okay, that's when it occurs. I'm gonna go like this. All right, so let's look at an example, okay? I'll have nitrogen with hydrogen, hydrogen, hydrogen here. So that's my NH3, okay? Very polar. Now what I need you to realize is nitrogen's going to share. I mean, they're going to share, but nitrogen's going to hog those electrons in all three. So just like what happened up above, right? We've got dipoles that do not cancel. We've got a partial negative here, partial positive down below, okay? Now, because this is why your hydrogen bonding is special, and this is why it's only these three elements, okay? Because nitrogen, oxygen, and fluorine are so small, and so electronegative, all right? Because of that, this nitrogen and sharing these electrons is sharing even more unevenly. So I like to explain it like this. The nitrogen has a partial negative charge that is on swole. So this is me, I've made this up, but it's kind of true, okay? But you can't use it in right? You can use it when you talk to me. Partial negative charge is like extra negative. Therefore, the hydrogen or the other side of the molecule has an extra positive. It's on swole. It's extra positive. Partially still, not complete, cation, anion. Now, what happens, and we are almost finished here, guys, is that I have another ammonia atom, which has a, let me draw that down here. Sorry, I have more room if I go down here. I'll put my nitrogen here, and I'll put a hydrogen here, and a hydrogen here, and a hydrogen here, and I'll put my lone pairs right here. Because, right, my dipoles point up here, making my partially negative end on swole here. Remember, once again, my partial positive was on swole. So my hydrogen bond is between these two ends of each molecule, right? Remember, sorry, I keep clicking on different colors. Remember that this is one molecule and this is another molecule. And we're talking about how one molecule is attracted to another. And this here, this partial positive of hydrogen and the partial negative, I'm going to get a different color, blue, of nitrogen, is the force of attraction. All right, this is your force of attraction. This is your intermolecular force, and it is a hydrogen bonding force because it is held between hydrogen in one compound and nitrogen in another compound. It is not a bond, but because of his extremely partial positive in one compound and his extremely partial negative in the other compound, this dipole attraction is particularly strong. So is particularly strong. And that only occurs when we have hydrogen attached to nitrogen or oxygen and fluorine in one compound. And then over here, we have hydrogen attached to one of those or a very electronegative element. Okay, it's confusing. I'm considering making this extra credit. All right, so let's look at that. If I have CCl4, what type of intermolecular force is going to hold it together? Draw it. This is tetrahedral. The dipoles cancel. This is nonpolar. It's got London dispersion forces. All right. This is H-Cl. Okay. This HCl, right? This is polar. It's linear. Dipoles do not cancel. Therefore, it's got dipole-dipole forces. This is water, right? H2O. It is bent. It is polar. Its dipoles do not cancel. Its dipoles are caused by hydrogen being attached to oxygen. So this is hydrogen bonding. Once again, or this is not the hydrogen bond. That is a covalent bond. The hydrogen bond would occur when this water molecule was attracted to another water molecule. That's the hydrogen bond. And it would be between the partial negative and the partial positive. It's confusing. Okay. See ya. I hope that those of you that are here, good job. Good job. Pat yourself on the back. Take AP Chemistry.